So this is Math 156, Lesson 7. And what I'm going to do is work out the solutions to the review problems for the first exam. So let's start. So problem 1 is to compute some limits. So let's start. Limit of 1 plus 1 over x. Actually raising this to the power x as x goes to infinity. So if I use capital L for limit, this won't give me the answer. It'll just write out the problem. And let me repeat that. Equals the same thing, but with a lowercase l. E. So this is an important fact that one definition of E, the number E, is 1 plus 1 over x raised to the power x. If we want to see this as a decimal, of course, it's 2.718. If we look at 1 minus 1 over x, we get 1 over e. And if we make it more interesting, 1 minus 35 raised to the power x over 28. You get x to the minus 5/4. And it's actually a very good exercise to figure out by hand why this is the right answer. Next, we have a sum. I write it with a capital S. And look at the sum of 1 over k cubed, as k goes from 1 to 100. Right, so I wrote down the problem correctly. Let me write the same thing for lowercase s. Ooh, I get something funny. See if I try to evaluate this as a decimal. So when I just had it as 1 over k cubed, it was trying to write this as a fraction, but it had a humongous denominator. This is over k. And suppose I want to take the same sum, but go from 1 to infinity. It's a little bit bigger. They agree to 5 significant digits. Then this is 07 and this is 5, 6, 9. Okay. That's problem 1. Problem 2 is to compute derivatives. So for example, if we have the function f of x is the sine of x squared, d of f is that function. Or I could write d of f of x is that. What about the second derivative? Well, I can do it in two ways. I could write d of the derivative of the derivative of f. That's that. Or I could write it evaluated. That's what it's equal to. Or the alternative way is d at 2 of f of x. And you see we get exactly the same thing. Suppose I take e to the x. So x goes to exp of x. Remember, you must write exp for the exponential function, not just the letter e. So if we differentiate this at x, this is what we get. And if we take the second derivative, we get something equally interesting. We get that. So here the function f of x equals 1 over 1 minus exp of minus x. That's what it looks like. Actually, it's an interesting function. If we plot f of x, this is what we get. So this is a function which is decaying and it's approaching the horizontal line. Y equal 1 is an asymptote. Approaches that line. What is the derivative of f? It's that. And what is the second derivative? It's that. Let's see if Maple can simplify that a little bit. Yeah, well, it's a tiny bit simpler. That's what it is. The next problem is the iterated logarithm. So f is the function, x goes to the log of x. And the derivative of f of x is 1 over x log x. And the second derivative is this curiosity. If we try to put it over a common denominator using the simplify command, we get this. For the arctangent, That's the derivative of the arctangent. That's the second derivative. It's by either the quotient rule or the chain rule. And here's a sort of a simple question. Suppose we take the tangent of the arctangent of x. What's the derivative? It's 1. Why is that? And then, of course, the second derivative is the derivative of a constant, which has to be 0. Of course, the tangent of the arctangent of x is x. Let's see if Maple will do that. If I ask Maple to simplify this expression. Yeah. The tangent of the arctangent of x is x. Because the arctangent of x is the angle whose tangent is x. And the derivative of x is 1. So that explains it all very nicely. Okay. Problem 3. Is to just play a little bit with the polynomial. So we have the polynomial x cubed plus 1 times x squared minus x plus 1 times x to the 4th minus 1. So we want to multiply it out, for which the command is expand. That's what it is. And then we want to factor this. And just write factor, parent sign, percent sign. Notice this is not what we got back. And the reason is because factor factors completely. This polynomial is not, these 3 polynomials can each be factored in turn. So when you factor it out, you get something like this. It's quite nice. Problem 4. So we have a polynomial of degree 6, which is x to the 6th minus 17 times x to the 5th minus 45 times x to the 4th plus 13 times, plus 132 times x cubed plus 5 times x squared plus 290 times x minus 456. Let's plot f of x. Now, f of x is a polynomial of even degree. So we know as x goes to infinity, f of x goes to infinity. So this function has to turn around somewhere and start to go up. So we have to go a little bit further to the right. Let's say maybe x goes from -5 to 25. Just 1x. So let's just go up to 20. So this function looks like this. It's not completely clear what goes on, but there clearly crosses the axis in here and here. Let's just blow it up in this range just to see what happens. So it looks like this crosses the axis at 1, 2, 3, and then 4 points. So 1, 2, 3, and then somewhere out here. So we want to find the solutions of the equation f of x equals 0. That means we want to find where the graph crosses the x-axis. And there are certainly places like here. So let me just blow this up and see what it looks like. So let me plot this maybe from, so it looks like maybe it actually crosses at -4. So from -4.1 to -3.9. Yeah, it looks like -4 is one solution. Now here we have a solution between 1 and 1.5. Let's blow that up. So it's really a solution between 1.2 and maybe 1.22, yeah. And between 1.213 and 1.214. Yeah, so here we have at least a 5 digits. 1.2134 is this solution. We also have a solution that looks close to 2. So let's plot this from 1.9 to 2.1. 1.99, 2.01. Yeah, it looks like 2 is a solution. And then we had one more close to 19. So let's just plot it from 18 to 20 and see what happens. So maybe 18.9 to 19.1. Yeah, it looks like there's one very close to 19. So let's see what Maple does when we just use the fsolve command. So fsolve the equation, f of x equals 0 for x. So it gives us -4, 219, and this other number. So we seem to have them all. That's pretty good. Problem 5, we want to plot two curves. So plot, and in curly brackets, One of them is 13 minus x to the 4, x squared over 40. That's a parabola opening down. And x cubed over 11 minus 8 times x plus 17. Oh, pretty. So we have this parabola and this cubic curve. Let me spread this out a little bit. Maybe x goes from minus 13 to 13. Yeah. So we see a little bit better. So this is this parabola, which is going down. And here's the cubic curve. And it looks like there are 3 points of intersection. So if we just wanted to find the x values, we could blow this up. Let's see. Suppose I try f solve. And the equation I want to solve So we do get instantly 3 solutions. Minus 9.75, 0.5, and 8.9. What are the y coordinates for these points? So let me just call these points A. So A1 is minus 9. A2, these are just in the order in which they're written down. A2 is this. A3 is this. Let's say we call the y coordinates B. So suppose we let B1 be what you get when you substitute x equal A1 into this polynomial. 10. Let's see, that looks like this should be approximately minus 10 plus 10. Yeah, that's what it is. What about B2 and B3? I just plugged them in. So B2 is the number you get when you plug in A2. And B3 is the number you get when you plug in A3. So roughly 10 and a half, 13, and 11. So this is about 10 and a half. This is about 13. That's about 11. I could also have written a loop for this. I could have said for k from 1 to 3 do. And what I want to do is compute b sub k. I need my n do. I know I just get the 3 numbers off once. It's purely a matter of choice how you do this. For problem 6, we want to use implicit plots, I need to open the plots package. I just put a colon so I don't need to see very much. So now I'm allowed to use the command implicit plot. And the first thing I want to compute, want to draw, is a certain ellipse, x plus 3 squared over 20 plus y plus 4 squared over 80 equals 1. Suppose I graph it for maybe x going from minus 10 to 10, y goes from minus 10 to 10. Oh, oops, didn't go down far enough. Let me just go from maybe minus 13 to 6. Huh. So it looks like a circle because it's not drawn to scale. But if I go to scaling constraint, there we are. That is the ellipse. Now there's another curve I want to plot, and I want to plot them together, but just for fun, I want to plot them separately first. This is almost the same, except there's a minus sign here, which makes this a hyperbola. It's looking more and more like a hyperbola. Okay, and then what I want to do is plot the two curves together. So one of these has a plus sign and the other has a minus sign. Let me do it to scale. There we are. That's what it looks like. So this egg-shaped curve, that's the ellipse, and here is the hyperbola. Problem 7, we have a curve and we want to find the tangent line and the normal line. So let me write this as a function. Let me just call it h, so just for a different letter. So h of x is square root of 31 minus x cubed. That's my function. And the tangent line, that's the line, and with the tangent line and the normal line at x equals 3, I take the derivative of h at 3 times x minus 3 plus the value of the function at 3. And the normal line a slope minus 1 over the slope of the tangent line. So this is the tangent line. This is the normal line, we hope. Let's see. Let's just plot h of x. Notice h of x, it's only defined where what's under the square root sign is greater than or equal to 0. So x cubed, this has to be greater than or equal to 0. That means x cubed is less than or equal to 31, or x is less than or equal to the cube root of 31. Now, let me draw it to scale. We also want the tangent line. So put in curly brackets. There is the tangent line. Yeah, there's the tangent line. And then I put in the normal line. That's the green line. And because it's drawn to scale, the blue and the green lines really do look perpendicular. Problem 8. We have the function, it's just a polynomial, x to the 4th minus 12 times x cubed minus 46 times x squared plus 12x plus 45. Let's plot f of x. Again, it's of degree 4, so it has to turn around and come up. So let's spread this out a little bit. Maybe x going from minus 5 to 20. Oh, so maybe just go to 17. So it doesn't go so far. Yeah. So it comes down, up, down, up. Load up in this region, just see what happens. Maybe from minus 4 to 2. Yeah. So in here, there are 3 zeros, 3 x-intercepts, and then this one. So what we can call x-intercept let me try it like this, x-intercept is what you get when you solve the equation f of x equals 0 for x. So actually, the x-intercepts are integers, -3, -1, +1, and 15. And the y-intercept is just where the graph crosses the x-axis, the y-axis. That's just f evaluated at 0. So this point is 45. What about the local maxima and local minima? Well, we need to know the derivative. That's the derivative. And you have to look for the critical numbers. I'll just call them, say, Cn for critical numbers. These are the points where the derivative of f of x equals 0. Solve that for x. We get these 3 points. Now, of course, you can tell by looking at the graph that at -2.1, you have a minimum. At 0.12, you have a maximum. And about 11, you have a minimum again. But we can use the second derivative test and compute, let's say, so for k going from 1 to 3 do, I'll put in my n do. And what I want to compute is the second derivative of f evaluated at the kth critical number. 4k, oops, from 1 to 3 do. There we are. Aha. Positive, negative, positive. So where the second derivative is positive, you have a local minimum. So minus 2.18 and 11.05 are local minima, and 0.12 is a local maximum. Right? Minimum, maximum, minimum. Minimum, maximum, minimum. What about inflection points? So for the inflection points, call them IP for inflection point, we want to solve when the second derivative is 0. And we get 2 inflection points, minus 1.8 and 7.025. Let's see. We have, this is convex up, convex down, and then convex up. So these are inflection points. So the curve is concave up from minus infinity to the first inflection point, and from the second inflection point to plus infinity. So on minus infinity to minus 1.08 and 7.08 to infinity. And concave down on the interval from minus 1.08 to 7.08. And you can see all of this on the curve. Concave up, concave down, concave up again. Okay. Problem 9. We have a sequence defined recursively as follows. U1 is equal to 1. U2 is equal to 2. And for n greater than or equal to 3, we have the following. So let's say for n from 3 to 30 do. And what we want to do is define un. And un is going to be equal to 3 times u n minus 1 minus 2 times u n minus 2. So for example, u3 is 3 times u2, that's 6, minus 2u1 is 4, minus 2, 6 minus 2. So u3 should be equal to 4. Let's see. Yeah, u3 is 4. So here's this calculation, and u30 is this number. That's the answer. Problem 10. Find the smallest positive integer where the sum of the reciprocals is bigger than 10. So let's do a little bit of experiment first. Suppose we take summation 1 over k. Maybe k goes from 1 to 15. Sure, I have it. Of course, I really want this as a decimal. So I go up to 15, it's about 3. If I go up to 100, it's 5. If I go up to 1,000, it's just 7. If I go up to 10,000, wow. If I go up to 30,000, it's bigger than 10. So let me write this in a nice form. Yeah. If I sum up to 30,000, I get something bigger than 10. If I sum maybe up to 25,000, well, it's still bigger than 10. What about 20,000? What about 16,000? What about 10,000? All right, let me do it the opposite way. If I sum up to 10,000, the reciprocals of the integers, I get 9.78. When I go up to 20,000, I get bigger than 10. So if I want to find the smallest integer, n, where the sum up to n is bigger than 10, this says it's between 10,000 and 20,000. So I don't want to look at every single number. I mean, let's see. If I made this 15,000, still bigger than 10. Huh. If I made this 14,000, too big. What about 13,000? What about 12,000? So I didn't have to do all this, but still it says that if I go up to 12,000, I get a sum which is less than 10. Up to 13,000 is bigger than 10. So I want to find the smallest k, the first time I get some number bigger than 10. So I could write something like this. For n from 12,000 to 13,000, do. And this is not the best thing, but it'll just be good for a start. So if this sum is greater than 10, then, so the sum from k up to n is greater than 10, then print n. And that's the end of the if. So this is going to give me a huge output, but let's see, let's just experiment a little bit here. If I went up to 12,500, oh, that's too big. I just want to get something that's not too big. I want to get an interval of just about 100 to look at. So here, this says that if I go up to 12,300 is too small, up to 12,400 too big. So let me just find the first time in this interval, it's only a length of 100, from 12,300 to 12,400, where the sum is bigger than 10. So maybe I should make this as a decimal. So it looks like 12,367 is the first time. Okay, so that's the answer. Yeah, let me just leave it at that. That's enough. There are better ways to do it, but this is, if it works, it works. All right. That was problem 10. And problem 11 is to count the number of primes that satisfy a certain condition. So let's say n is going to be, or let's say k is my counting number. And I let k equal 0 to start. And then I want to count primes up to 1,000. So for n from 1 to 1,000 do, and what do I want to do? If a certain number is prime, n squared plus 7 is prime, then I want to add 1 to k. So I replace k with k plus 1. So every time, if I go through the first 1,000 numbers n, every time n squared plus 7 is a prime, I add 1 to k. And when I'm all done, I can say print k. The answer is there are 167 such primes. Good. That is everything on the review sheet. So we are done for today.